Hi, NA Physics, it's Mr. Neff. This is my second video on coupled masses. Let's get into two more examples with coupled masses, but before we do, what do you call an alligator in a vest? I'll tell you about that at the end of the video. Hey, look at this. Our friends over at OPhysics have this nice simulator that will do a modified Atwood's machine. So remember, the Atwood's machine is whenever the two masses are hanging straight down from the pulley. This time, you have a pulley with one mass hanging down, and you have another mass over here on the tabletop. Now, I can set this the way I want. I can put friction in there if I want there to be friction, or I can set the coefficient of friction all the way down to 0, which I'm going to do. I can mess around with the size of the masses and so forth. And at the end, I can even check what values are the correct values. So take a look at this. The mass up on the tabletop, they're calling mass 2. It's 10 kilograms. The mass that's hanging, they're calling mass 1, and it's 5 kilograms. And so you'll see that if I run this, the two masses have the same acceleration. They're coupled together. There was a net force on the system, and it accelerated. So what I would like to do, just like I did in the last video, I would like to figure out what is the acceleration and what is the tension in that string. So just like last time, first step on this is going to be draw a free body diagram for both objects. I want you to pause the video and draw a free body diagram for both. Okay, look at what I did. On the hanging mass, mass 1, I put a tension and a force of gravity. I already saw it accelerate. I know it accelerates down, so the force down has to be bigger. Over on the other mass, I put the same size force of tension. Remember, with a lightweight pulley, frictionless pulley, you can't stretch one side of the string more than you stretch the other. So tensions are going to be the same size. Not really important to this problem because there's no friction, but the Y forces are there. I got a force of gravity that's twice as big as the force of gravity on the other one, and I have a normal force that's real big too. I don't care about those that much because there is no friction. If there was friction, it would be pointed backwards like so, right? Force of friction. I'll just leave that there even though the value of that's going to be 0. But if there were friction, it would be there. And then I would need the normal force to figure out how big the friction was. As it is, there is no friction in this case. All right, so now what I'd like to do is I would like to do F equals ma for both objects. So if you will take and stop the video, and just a hint, I want you to use this tension, this force of gravity, these masses. Remember, the mass 2 is 10 and the mass 1 is 5. And I want you to do F equals ma for both. Stop the video right now, please. Okay, we're back. So now, for the one that's on the tabletop, I said sum of the forces equals ma. Now, I only looked in the x direction because that's the direction of the acceleration. And the only force I have there is tension. Now, if there was friction, I would go minus friction here, but that isn't there. So I'm going to get rid of that. On the other side, I say sum of the forces equals ma, and I'm looking in the y direction. That's the only direction that we have acceleration there too. Now, I didn't think about up and down. I thought about which force is winning. That's the force of gravity, and which force is losing. That's tension. And that's equal to m1a. So this is 5 kilograms, so it weighs 5 times 9.8, or 49 newtons, minus the force of tension, unknown, equals the mass 5 times a. Now, you see my two equations in the boxes. That's a system of equations that's pretty simple to solve using substitution. Stop the video here and solve that. Okay, we're back. So now what I'm going to do is I'm going to take my 49 minus the tension, which I'm going to say is 10a, is equal to 5a. So that's going to be 15a equals 49. And I've already done this. I know that the acceleration is 3.27 meters per second. Then, if I want the tension, all I got to do is take that acceleration and put it into either one of the two boxed equations. The blue one's super easy. So I'm going to say that the tension on both sides is 10 times what the acceleration was. So it's going to be 32.7 newtons. Now we can go back over to the simulator and check that. You can see that we can put the values on there. There's the acceleration that we found, very nice. There's the tension that we found, very nice. Now one more example for this video, and I have two more coupled masses. There they are tied together, sort of like what we've had. This time there's no pulley or anything. There's no change in direction to throw you off or anything like that. The two identical boxes, both being pulled across a horizontal floor at constant velocity by a horizontal pulling force of 176 newtons. So maybe an applied force of 176 newtons. It says there is friction between each box and the floor, and you're supposed to find the tension in the rope between the boxes. Okay, so the free body diagram for each one is where we're going to start. So please stop the video, try to draw a free body diagram for each. Okay, we're back. So we have the applied force on the right box. We have tension on the right box too. It's going to go back like this, and I made it a little smaller. I made it a little bit smaller because, not because we're accelerating, because we're not. It says that there's constant speed, but I also have to have a friction on there too. Now there's tension on this one too, and there it is. Okay, now I also have to have friction, and the friction, the kinetic friction, is going to be backwards on both boxes, and so I'll draw that back here like this. And since the boxes are the same size, made out of the same stuff, they're on the same surface, I'm going to draw the other one the same size as that too. So just trace that over, and so we're going to call that force of friction kinetic. Okay, now you can see that the force of friction kinetic must be equal to the tension. I'm saying that because if we're moving at constant velocity, then that means we have no net force, and so that means this force has to be the same size as that one. Okay, good. And so then that means that if those two are the same, then that means these two are the same, because the two tensions are the same size as each other, the two frictions are the same size as each other, and so the two blue forces are the same size, the two red forces are the same size, and so red and blue are the same size, so I really only have two size vectors there. I got the big applied force over on the right, and then all the vectors to the left in the picture are the same size. So what do I have here? I have two forces, call them F size. One's tension, one's friction, I know, but that's equal to 176. I know it must be because the right one is also at constant speed. So that says that that force is going to be 88 newtons in size. So we got 88 newtons here, we got 88 newtons here, 88 there, 88 there. They were asking what's the tension in the box, or the tension in the string between the boxes. Hey, it's 88 newtons. So I hope that you learned a little bit about coupled masses, and maybe you feel even better than you did at the end of video 1, certainly before you watched video 1. And before what do you call that alligator in a vest? An investigator. See you next time.